So the last part of chapter 9 is actually going to have us go back and work on something from chapter 6 when we talk about enthalpy. Now before we were talking about enthalpy, and enthalpy is our delta H. And it's related to our reaction, the amount of energy that gets transferred, similar to heat. Now, our enthalpy, we could find that using things like Hess's law or the heats of formation. But now that we know how to do our Lewis structures, we can also find it from something called bond enthalpy. Now, the idea behind bond enthalpy is that multiple bonds are stronger than single bonds, and that different bond connections between the different elements or atoms will have different amounts. So we can measure an average bond length for different bond types, and we can start to relate that to bond energies. Now, the idea is that as the number of bonds between the two atoms increases, our bond length decreases. So you can see that our triple bond is going to be our shortest bond. Our single bond is going to be our longest. As we add more bonds, that distance closes. And the shorter the distance between those charges, the stronger that bond. So the more energy it's going to require for us to break it apart. Now, chemical reactions involve breaking bonds in reactant molecules and making new bonds in the products. So the delta H, or the enthalpy change for our reaction, can be estimated by comparing the cost of breaking all of the old bonds versus the ones that we get from making the new bonds. Now, the amount of energy it takes to break 1 mole of a bond is called its bond energy. And the idea is that it's what we take in our gas state, so that way we can homolytically split it. So that's, if we have a nitrogen single bond to a nitrogen, we're going to split that bond in half, and each of those nitrogens is going to leave with 1 of those bonding electrons. In general, the more electrons the two atoms shares, the stronger that bond is. And so when we compare bond energies, the triple bond takes more energy to separate than the double bond, than the single bond. And that doesn't matter whether it's between carbons or whether it's the carbon and the nitrogen, that trend stays true. Now, a single bond is not half as easy as a double bond. And so they don't exactly scale up in that way. So the amount of energy to break a double bond is not twice as much as 2 single bonds. That part doesn't hold true. The idea is, in general, the shorter the covalent bond, the stronger the bond. The stronger the bond, the more energy it should take us to break them apart. But it only works when we compare similar types of bonds. So for bromine to fluorine, or bromine to chlorine, and bromine to bromine, you can see that the distance is decreasing down that column. And so our bonds are going to be getting, our distance is increasing going down the column, and the bonds are getting weaker and weaker. Bromine is larger than fluorine, and so a bromine to bromine bond is going to be longer than a bromine to fluorine. Bonds also get stronger across a period as their bond distance shrinks as well because of that electronegativity differences. So we can use this method to estimate a delta H. Now, the part to remember with this is that they end up being a slightly different formula than our normal one. Our normal reaction is delta H is the sum of our products minus the sum of our reactants. When we're doing average bond enthalpies, the part to remember is that we always are given the energies as being positive. It's how much energy we have to put in there to break. So all bond breaking is endothermic, so our delta H should be positive. And all bond making is exothermic, so our delta H is negative. So we end up with a different kind of reaction equation. Because when you think about our bonds being broken is kind of like our reactants. And the bonds being formed is kind of like our products. And so in some ways it feels backwards from all of the other ones. And it's backwards because we have to put in that energy to break our bond. So we have to break apart all of our reactants first, and then we can regain that energy when we make those products. Kind of like this diagram here. So we're going to split apart all of those bonds, and then we'll reform them at the end. Now the challenge was before we didn't know whether we had single bonds, double bonds, or triple bonds, but we should be able to do that now. So if we have methane, CH4, we should know that methane now, based on its Lewis structure, is 4 single carbon to hydrogen bonds. Our chlorine is a single chlorine to chlorine bond. And CH3Cl, we know that that is going to be 3 single CH bonds, 1 C to Cl, and 1 H to Cl bond. So now when we look at that difference, we can tell that we need to break apart one of these carbon to hydrogen single bonds. We need to break apart one chlorine to chlorine bond. And then we need to form a new carbon to chlorine bond and a new H to Cl bond. So when we want to find that delta H for that reaction, then we can find that by taking our bonds broken, C to H plus ClCl, and we can subtract from it our bonds formed, a C to Cl and an H to Cl. Once we know those average bond enthalpies for that, we can plug those in, we can find those new ones. This method's not quite as precise as some of the other ones, and it's generally because we're finding just an average bond length. So different compounds will have different bond lengths because there could be other things attached to it. And so we're just using the average bond lengths when we look for them. And so this is a picture where we can see our bond lengths for our F2 versus that of our chlorine versus our bromine. And you can see that as we go down the column, our bond lengths are increasing in their length. And so while the length is going up, our energy should be going the other way. Because the shorter the bond, the more energy there is inside of it. This is an example of some of your average bond lengths. And so on the quiz or an exam, if I wanted you to solve for the enthalpy change for bond energies, then I would have to provide these with you. And so what they do is they measure these average bond lengths and energies across several different compounds that have that same type of bond, and that's how they're able to build this kind of table for us. Now, the other part we wanted to talk about was our metallic bonds. And so our metallic bonds, these happen because there's low ionization energy of the metals. So they lose those electrons easily. And so we have this sea of electrons. So the bonding results from the attraction of cations to the delocalized electrons, similar to this. Now, this theory isn't really as commonly talked about in Lewis structures because we don't really have a Lewis structure for the metals. But it does imply that because the electrons are delocalized, then they should be able to move throughout the metallic crystal. And how we know this is that metals conduct electricity even though they're solid. So that means that even though they are solid, and that means that our electrons, our nuclei of our metals are stuck in place, we still see a flow of electrons from one side of the solid to the other, which gives us that idea that the electrons are delocalized. They're not attached to one specific nuclei of the metals. It really gets shared between the whole structure, that solid structure. This also shows up with our heating conductivities. Or this concept that as we increase the temperature, then there should be less electrical conductivity. The idea is as we heat the metals, the metal ions are going to vibrate. The more they vibrate, the harder it is for those electrons to travel back and forth. It's kind of like if you were walking across a rope bridge. The more that bridge is shaking, the harder it is for you to walk across. If that bridge is very stable, it's a lot easier for you to walk across. So as those metals vibrate around, it's harder for those electrons to migrate back and forth between them. And we see this in that as the temperature increases, our electrical conductivity of metals decrease. It's one of the problems that we see in computers or electronics is if they start to overheat, they start to degrade in their processing ability because their electrons are not going to flow correctly. It takes us more energy to send them across. Heat is a form of kinetic energy, and so the more the model of this idea of our light electrons moving around through the metallic solid means that we should be able to transfer kinetic energy as well, because those electrons are able to move freely, and so they should be able to translate that kinetic energy for us. So we predict that a metallic solid should conduct heat well, because those, while the nuclei are kind of stuck in their solid position, we have those electrons that can move around in between them. So instead of everything being locked in position like a covalent molecule, we still have those electrons that can flow freely. And this is one of the reasons why a metal cup is not great to drink hot water out of, because when you pour the hot water inside, your metal cup will conduct that heat very well, and we'll feel that on the outside quite quickly. The last couple parts that we're going to talk about with our metallic bonding is one of them is this idea that they reflect light. Light's being reflected because while we have these delocalized electrons, the delocalized electrons on the surface can absorb the outside light and then emit it back. This happens because those atoms are emitting light when the electrons are jumping from high energy levels to lower energy levels. And because the entire system shares a same set of orbitals, then we should be able to absorb and reflect on the surface all of that light as well. And that's part of the reason why metals seem so shiny, is that they're doing such a good job of reflecting out all of that light that gets absorbed and emitted from the entire solid of the metal. And since our attractive forces that are holding those metals are delocalized between them, it means that we can easily move those atom cores around, and the electrons will still be able to maintain that attraction. This makes us quite malleable or ductile. That means that we can fold, or we can bend metal, or we can shape metal, and it still is hold together, right? It's not brittle, it's not going to crack. So when you take an ionic solid and you hit it with a hammer, that solid will hold together quite well, but eventually it's going to start to break into pieces. But that structure is very rigid because those cations on those anions can't shift around, because both of them are fixed. The positive and the negative is fixed. On the other side, the electrons in the metal are free moving. So as we move those cores around, those atomic cores, the positive sides, those electrons can move freely between them in order to adjust. Because it's such a strong attraction between all of those delocalized electrons and the stability that we have because we can spread those electrons out through all of the different metal cores, then it means that we should have a high melting point and boiling point, which we do see. They're not quite as high as an ionic solid, which is why we do have some metals that are liquid at room temperature, mercury, for example. But it does mean that they are stronger than our covalent molecules, where we have significantly more of those that we find that aren't solids at room temperature. So remember that when you're trying to look at metal solids and their trends, the melting point should increase as we go left to right across the period, because the charge of the cation is increasing. So that means that the more positive those or those atomic cores are, the stronger the forces holding them together. And then it generally decreases going down the column because they're getting larger and larger. So there's more space between those metals, and so their strength is not as strong. So that's why we're decreasing going down. So when you're trying to go through, your simplest approach is remember that the metal and the non-metal is ionic. A non-metal and a non-metal is covalent. Metals and metals are going to be metallics. Now, there are a lot of different exceptions to that. And so you do want to be paying attention to that. And so one of the things to go back to is your electronegativity differences. So properties of compounds are often best and so you're using your electronegativity differences. You can get an idea about whether something's going to be ionic or covalent. And so I'll show you how to do that in a second. And then another thing to look at is look at your properties of your covalent compounds. The lower melting points mean covalent bonds is an example of that. And so you want to start to piece together some of these things in order to get an understanding about what kind of chemistry is going on between them. The more we can understand about the bonds that are holding the bonds that are holding the atoms together, the easier it will be when we start trying to predict their responses. I'm going to link a video here, which I think is very good, talking about ionic versus molecular compounds. So if you're still struggling with that part, then go ahead and you can watch that video. Remember that we do have these electronegativities. The higher the number, the more electronegative it is. The more electronegative it is, then the more likely it is going to be to absorb, or the more it wants to gain an electron. Now, a pure covalent bond is going to be something that's very close to zero. That difference is actually in the 0 to 0.4 in their electronegativity difference. That means those electrons are pretty much shared evenly by all of those atoms. As that difference in electron negativity increases, then we start to see a side that doesn't quite get that electron pair as much. It starts to become a little bit more positive. While the other side gets a little bit more of that electrons, they start to become a little bit more negative. That happens from 0.4 all the way over to that 1.9-ish type of range. You're seeing different places that this range is somewhere between 1.7 to 2.0. Because covalent to ionic bonds are kind of on a spectrum, you see where that cutoff is varies slightly differently. And so you, for our class, we'll take anywhere from that 1.7 to that 1.9 is kind of being our cutoff. Anything more than that, we have an ionic bond where we're believing that the electron, instead of being shared, is much more like it's being transferred. And so this difference is going to start to build polarity. That means that we're getting a positive side and a negative side, or a partial positive and a partial negative. So this stands for partial. It means that it's not quite a complete charge transfer, but is building there. And so we call them poles because you have a positive side and you have a negative side. So those poles that are developing are why we call this polarity. I'm going to let you practice those. You want to practice identifying these partnerships and using this chart over here to identify whether they're going to be polar covalent, non-polar covalent, or ionic. And so remember, the larger that electronegativity difference, the more polar it is. The more polar it is, the more ionic it is becoming in character. The less polar it is, the more covalent it is becoming in character. Now, most bonds have some degree of sharing and some degree of ion formation in them, so that's their bond polarity. The more polarity we have, the more close to an ionic bond we are moving towards. So this becomes important as we start looking at our molecules. as we look at molecules, we're going to be using this bond polarity in our next part when we talk about this dipole that forms. So dipoles form when there's an unequal distribution in that sharing of those electrons. In the same way that we're starting to classify things as being polar covalent, we're going to use that in our next chapter when we get into the intermolecular forces. Another way for us to talk about that is the percent ionic character. And so percent ionic character is percentage of the bond's measured dipole moment compared to what it would be if it was completely transferred. So if it was 100% ionic, it would be 100% transferred, right? So that's us being an ionic bond. If it's 0% ionic character, then it's purely covalent. And so all bonds will fall somewhere between that range. The lower the ionic character, the lower the percent ionic, the less bond polarity we see. And that pretty much covers up all of our chapter. Go ahead and start practicing with your identifications. I have the answers for your polar, nonpolar, and ionic on slide number 60, so you guys can see that as well. The other part is you want to make sure that you finish up your study assignment B. That is the big part for this chapter, is being able to draw your Lewis structures, identifying proper resonance structures, formal charges, and using that to get to our next part, which is our proper molecule shapes.